Hi, my name is Joseph Watt, and today we're going to be looking at connections between algebra and geometry. So for today's lesson, I did pull an example straight off of one of our older homeworks. It says to determine k so that the line is parallel to the given line, which in this example is 2x minus 3y plus 18 equals 0. So to be trying to determine what a parallel line would be to that, we're using the following manipulatives. So on here we have an x and y axis that I have graphed out together, and we're going to be using string to try and help prove a couple things. So I already broke down this equation into the slope-intercept form in order to be able to quickly visualize it on here and map it out or graph it out quickly. Now we could use the slope-intercept form and quickly determine what is the slope, but instead we're going to try and eyeball it and see if we can find a relationship between these points on here. So assuming that these are whole integers, we're going to try and determine what is the slope just by looking at it. So on here I can see it looks like we should be going up 2 over 3, there's a point, up 2 over 3, there's a point. Let's make sure it stays true, up 2 over 3, okay? So based on just eyeballing this manipulative, it looks like our slope should be 2 over 3. And according to the question, we're trying to make k so that it is parallel with this line. Okay, so we have to try and figure out how to determine if the line is going to be parallel or not. Well, first we need to know what is parallel. So hopefully we know that parallel is when you have two lines that are never going to cross over or intersect or get any closer to each other. So I think the easiest concept to imagine is the railroad tracks. Each side of the railroad track will never get closer or further from each other. They will stay in straight lines, equidistant apart, always, forever. So there's two parts of a line here on this graph that I think we could try and look at. So first thing we could look at is perhaps the y-intercept. Could we use the y-intercept to determine if k would be parallel? Well, let's use a point on the y-intercept. It doesn't really matter where, let's just pick one. Here's one on the y-intercept. And if we're going to try and make it look parallel, that looks pretty close. But if we move the y-intercept, does that not also look pretty close? Now the lines are drastically different from before. So I think that can pretty quickly rule out that the y-intercept is the determining factor on parallel or not. So what's the other concept? The other concept is what we've talked about is the slope. Okay, well, let's try and see if the slope will help us determine whether or not lines will be parallel or not. So we've picked a whole integer here, and if we're going to use the slope, I'm going to put it where it looks about parallel. That looks pretty good. And we're going to count. We're going to use the same slope, 2 over 3, and see if it looks about right. So we're going to go 2 over 3. That looks pretty even. 2 over 3. That looks pretty even. Let's check one more time. 2 over 3. And that looks pretty even. So far it looks like we've eyeballed it about right. And that would help show us, or bring us to the conclusion that the slope, if the slope is equal, it looks like the numbers are going to be parallel. Or to think of it another way, another thing you can think of is if you have two equations that have an equal slope, we know that those equations are going to create lines that will be parallel. Okay, so the last thing we want to touch on with this manipulative is what's the opposite concept of parallel while we're on the subject? Perpendicular. Okay, so perpendicular. We know the parallel is determined by the slope. If we're also going to try and figure out if something is perpendicular, how can we figure that out? Well, first we need to know what is perpendicular, just like parallel. Perpendicular, if you remember, perpendicular is when two lines cross at a 90-degree angle. So they have to be perfectly square, the cross that they create. All right? So if we've picked a point on here, like I've just placed the pin in there, I'm going to wrap it around. I'm going to wrap it around the yellow tack, and the yellow tack will be our starting point. That will be the string we can adjust. And we need to try and figure out where is going to be perfectly perpendicular. So the first thing that I would notice on here is if we have perpendicular lines, we can see the first line we had is positive, right? It's moving in an upward slant, it's positive. So if we have a perpendicular line, we can already see that no matter what this number is, if it's positive, perpendicular is always going to be negative. With perpendicular lines, you're going to have one positive and one negative number always. Okay? Now, we know that the slope was the determining factor on parallel lines. So I think it's safe to assume that the slope probably has something to do with the perpendicular line as well. So let's just try and take maybe a semi-educated guess. What could be the relationship for a perpendicular line? We know that the slope has to be the same for parallel. Well, what if we just stuck a negative on the slope? Do we think that that might possibly create perpendicular? Well, let's take a look at it. We said that this looks roughly perpendicular, so let's count off -2/3 and see where it lands us. -2/3, -2/3, -2/3, +3. So it looks like we're starting to get way off track from where we think is perpendicular. So this educated guess is not going to work, huh? Well, let's try and eyeball it and see if we can just decide what the determining factor or what the relationship would actually be. So let's try and eyeball and count like we did last time. It looks like there's a whole number down here, so that would be -3/2, -3/2, -3/2. Looks like they're falling on a dot pretty much every time. So we're saying -3/2. Well, what's the relationship between these two? Well, we do see a negative, like we originally guessed. But the other relationship we see here is what's called the reciprocal. Or you could just say where the fraction's flipped. So based on this manipulative, it's safe to come to the conclusion that in order for something to be not parallel but perpendicular, those two equations are going to have slopes where the relationship is reciprocal of each other as well as the opposite sign. Not necessarily negative, but just the opposite sign. So if you have two equations that have the opposite sign of each other and are the reciprocal of each other, we can already determine that those two equations are going to end up being perpendicular by the time we graph them.